Hello everyone. I'm pleased to represent our team to present our recent work on model predictive temperature balancing control for lithium-ion battery modules based on a generalized thermal network model. Unlike our previous studies focused on single-cell analysis, such as the work presented at ECCE last year and our recent publication in the IEEE Transactions on Power Electronics, this study investigates battery modules composed of multiple cells. We believe the proposed model can be extended to various types of lithium-ion battery modules and even beyond lithium-ion batteries. Advanced but lightweight AI technologies are integrated to enhance model accuracy to ensure compatibility with embedded control system implementation. This slide shows the outline of my presentation. First, I will give a brief introduction to the existing thermal issues in lithium-ion battery modules and review this classic electrical thermal model for a single lithium-ion cell commonly used in embedded control systems. Next, I will discuss how this single-cell model can be extended to a multi-cell thermal network model, following the fundamental principles of modeling thermal phenomena, not only in battery systems, but also in other power electronics applications that require simplified representations for embedded control. Based on this thermal network model, I will explain the perimeter identification and introduce the proposed temperature balancing control strategy for multi-cell modules. Then, I will present experimental results that validate both the accuracy of the model and the effectiveness of the control approach. Finally, I will summarize the key findings and outline directions for future work. Lithium-ion batteries are ubiquitous, powering everything from everyday portable devices to electric vehicles. Their high energy density makes them exceptionally popular. However, several challenges still hinder their performance, especially in fast charging applications. Under electrical stress during rapid charging, lithium-ion batteries can overheat, potentially leading to irreversible thermal runaway and thermal propagation that affects neighboring cells. In addition, detecting hot spots or early-stage failures remains difficult due to the limited number of temperature sensors typically available in a battery module or pack. Building electrothermal models for lithium-ion battery cells is an effective way to create virtual thermal sensors within a module or pack. Electrothermal models for single cells are already well established, including our earlier work published in 2018. This figure shows the equivalent circuit diagram of a classical single-cell electrothermal model, which typically consists of two interconnected parts. An equivalent circuit model representing the electrical behavior with both static and dynamic characteristics, and a corresponding thermal equivalent circuit that describes the relationship between heat flow and temperature. The coupling between the electrical and the thermal domains is generally achieved through the Bernardi equation, while recent studies also introduce a temperature feedback link to improve model accuracy. Although various derivatives of this model exist, its simplicity and ease of implementation in embedded control systems make it uniquely effective compared with other modeling approaches for single cells. The hybrid pulse power characterization test, conducted under different ambient temperatures, is commonly used as an efficient method to identify the model parameters. We begin with the proposed thermal network model, which represents how heat is transferred and accumulated within a battery array with 4 cells, shown in this figure. In this model, each cell is treated as a thermal node that exchanges heat with both its surroundings and the neighboring cells. The heat dissipation from a cell to the ambient is represented by RBI. The thermal coupling between adjacent cells by RBIJ. And the thermal capacity of each cell by CBI. The model is constructed based on 4 assumptions. First, each cell is assumed to have a uniform temperature, represented by a single lumped thermal capacitance, which is reasonable given the slim geometry of the studied lithium-ion batteries. Second, each cell exchanges heat with the ambient environment through a thermal resistance. Third, thermal conduction occurs between the neighboring cells. And fourth, the ambient temperature is assumed to remain constant. These assumptions enable the thermal network model to approximate complex heat transfer using a simplified circuit representation. Now that we have established the physical structure of the model, we can examine how it connects to the experimental setup and how it is used to characterize temperature variations across the battery array. Here is an overview of how the thermal network model connects the physical experiment to the simulation. On the left, we show the experimental setup, where 4 lithium-ion cells are instrumented with thermocouplers to measure temperature variations across the array. The thermal simulation beside it illustrates how uneven temperature gradients develop during operation, highlighting the need for a coupled model. Each blue bar represents a thermal node corresponding to a cell, where the surface temperatures TB1 to TB4 are measured. These nodes are mapped to the equivalent circuit on the right. The model serves 3 main purposes: to capture inter-cell temperature variations, to enable current optimization for uniform heat distribution, and to mitigate degradation caused by thermal imbalance. To ensure the model is predictive and accurate, the optimal parameters of the thermal network are identified using a Bayesian optimization approach in this work. Our objective is straightforward: to fit the model temperature curve to the measured one. The parameter vector, denoted theta, contains the branch resistances and capacitance, RBI, RBIJ, and CBI. The error is quantified using a mean square difference between the measured and modeled branch temperatures across all 4 nodes and time samples. The optimizer then searches for the parameter set that minimizes this error. However, directly evaluating this error is computationally expensive because each trial requires a full simulation of the proposed thermal network model. To overcome this, we apply Bayesian optimization, which builds a Gaussian process surrogate of the objective function. This surrogate allows the algorithm to explore the parameter space intelligently while reducing the number of simulations required. The process begins with a few randomly sampled parameter sets whose true errors are evaluated. These results are used to construct the Gaussian process model, which predicts both the mean and uncertainty of the objective across the search space. We then use an acquisition function, specifically the probability of improvement, to select the next candidate that balances exploration of uncertain regions and exploitation of promising areas near the current best result. The algorithm iteratively updates the Gaussian process model after each new evaluation, continuously refining its understanding of the error surface. This cycle of sampling, modeling, and updating continues until improvement becomes negligible or the iteration limit is reached. As shown in this diagram, the Bayesian optimization algorithm proposes new RBI, RBIJ, and CBI, runs the thermal network model simulation, compares the modeled and measured temperatures, and feeds the resulting error back into the surrogate model. In summary, this Bayesian optimization-based approach enables data-efficient parameter identification, achieving accurate model fitting with far fewer simulations than traditional grid or random search methods. The results presented here show the identified parameters of the thermal network model for the 4-cell battery module, with the key parameters listed in this table. The parameters obtained using the Bayesian optimization are compared with those identified using the differential evolution algorithm, a well-established global optimization method. The close agreement between the two sets of results suggests convergence toward the global minimum of the error function. The reconstructed temperature profiles at the bottom demonstrate excellent consistency between the measured and modeled data, confirming that the thermal network model accurately captures the thermodynamics of the battery array. The curves represent the natural cooling of the cells, where the heat generation is negligible. The model achieves root mean square errors of 1.6% for the Bayesian optimization and 1.7% for the differential evolution. With the model now well identified, it can be integrated into a predictive control framework to actively regulate cell temperatures during charge. With the thermal parameters identified, we embedded the thermal network model into a model predictive temperature balancing control. The goal here is to use the model in a predictive manner to estimate how each cell's temperature will evolve under different current conditions, and to adjust the control input accordingly. The power stage is implemented using a single input, multiple output switch capacitor converter. This topology allows multiple cells to be charged from a single source while still enabling independent current control for each cell. The control structure operates in two layers. The master controller determines the overall charging current based on system-level requirements and feedback from the module. The slave controller then distributes this current among the cells, guided by temperature predictions from the thermal network model. Using these predictions, the controller solves an optimization problem at each step to minimize future temperature deviation and current ripple while maintaining the desired charging rates. The thermal network model effectively acts as a digital thermal twin within the loop, continuously predicting the transient temperature response, updating state estimates, and providing the controller with the foresight to take proactive action rather than reacting after temperature rise occurs. This new control framework combines model-based prediction with real-time current coordination, leveraging the identified thermal network model for smarter and safer charging control, without adding complex or high-cost sensing hardware. The experimental setup consists of a thermal chamber to maintain a controlled ambient temperature, along with a data logger, cell tester, and other supporting equipment. A simple fixture is designated to position the cells at equal distances from each other during testing to ensure uniform thermal conditions. We validate the proposed control framework using a 4-cell module with a 1 mm spacing between the cells. Under an ambient temperature of 23.5 degrees. The total current was limited to 12 amperes. On the left, under conventional constant current charging control, we observed a temperature difference of about 3.2 degrees after 20 minutes, as shown in both the temperature plots and the infrared image. On the right, with the proposed model predictive temperature balancing control, the temperature difference was kept within 0.5 degrees throughout the charging process. These results confirm that the proposed control can effectively maintain thermal uniformity and minimize the risk of local overheating. In summary, this work presents the development of a thermal network model for efficient prediction of cell temperatures in battery modules. The proposed model effectively captures inter-cell thermal coupling while requiring significantly lower computational efforts than finite element methods. Bayesian optimization is employed to identify the model parameters, achieving accurate fitting with fewer simulation iterations.
Furthermore, a model predictive temperature balancing control is integrated with the thermal network model to enable predictive current control, demonstrating superior temperature uniformity compared with conventional control schemes. The proposed model and the control framework are experimentally validated on a 4-cell module, showing reduced temperature deviations, enhanced safety, and mitigated degradation due to the thermal non-uniformity. More detailed discussion of these technologies can be found in this recently published journal paper.